Now we come to a very important discussion of work energy theorem. I will just remind students that this work energy theorem is applicable only where only applicable for non-conservative fields. It is important that the work energy theorem is applicable for non-conservative field and for non-conservative forces rather. So that is very important that for non-conservative forces, the work energy theorem will act. Now, the fundamental point in work energy theorem lies in the fact that work and energy are interconvertible and are two sides of a same coin. So that is a very important aspect. Work and energy are interconvertible and are two sides of the same coin. Now, what we need to do here, I'll show you with an example that how this system works with distributive forces. And I will take a specific example to explain the whole thing. Say, for example, I have an incline here, and the incline has a height h and an angle theta here. And the incline is divided into two parts, having a first half which is smooth. There is no coefficient of friction here. This is smooth. And the second part is rough. So we have friction here. And then the length is divided into two equal halves. It is L and L. We are dividing the length into two equal halves. And then I have a body of mass M, which is primarily at rest here. I release the body and I find that it comes back here and is again at rest. Now, this is the scenario that I have. So I will explain the scenario again. It is an inclined plane that has two portions. One is smooth, having mu 0, and the other is rough. There is a coefficient of friction here. And they are equally divided into two sections, L and L. And I release the body from the top of the incline at rest. And as I find that as it comes to the bottom of the incline, it also is at rest. So the question is, what is the value of the coefficient of friction? Now you see, in order to solve this problem, if I apply the conservation of energy at points A and B, then I find that energy at A is mgh and there is no kinetic energy, so it is 0. And at B, both potential energy and kinetic energy is 0. So you see, the conservation of mechanical energy do not apply here, as mgh have just vanished into the blue in this case. So where it should have gone? We are suggesting here that this work or this energy has got converted to the work done by the friction force. So that is the essence of work energy theorem. You see, this energy actually got used up by the work done by friction. So and then we can go on to write something else. We can put it like this, that mgh which is equal to mu mg cos theta into L. So that's very important. That is the work done for the friction force part. And then h can be represented as 2L sin theta from the graph or from the incline. So it is mu mg cos theta into L. And then from here on we can go on to calculate mu, which happens to be 2 tan theta. Now the answer, I repeat, is not very important. What is very important is the approach and this particular element where the energy part is converted to the work part. And the work part is performed by friction, while the loss of potential energy of the body is used up by the friction, which is doing work here. So that is all for now regarding work energy theorem. Thank you, students. For testing your understanding of this lesson and more videos, log on to www.tubelessons.net.